transformer. That's all it is. But it's typically a transformer that we wind, and I've made one of these, I believe. Usually you get a ferrite donut. Think of a donut. And you take two pieces of wire that are shellac or insulated. So here's my ferrite donut. It's going to be made of iron. All right? Dimensions in this case are important. I'm not going to ask you to calculate inductance. And you're going to have a wire that's going to curl around this way, come out this way. And you're going to have another wire that is going to curl around the same way. In other words, what I'm doing is wrapping them in this direction, counterclockwise, looking straight down. It has to wrap in the same direction, so it's like this. You all with me? Now, you all know in general, when you put a signal in, you put a plus to minus voltage if you have an extension cord, a transmission line, any kind of a communication device. It's in a differential mode where current goes down one wire and back the other. Isn't it? Do you all follow me on that? This is standard. Okay? So when we do this, we're going to call this I1 here, and we'll call this I2 here. These are just two currents that come in. Obviously, this is going to be I1 coming here, and this would be I2. You all agree with that? Now we got a coil of wire, right? First thing we have to make sure, and I think how many have had Dr. Gross? Well, Dr. Gross loves doing this, and I'm going to do it too. He says if you just have a long iron bar, assume it's infinitely long, and you take wire and you wrap it like this, and you take wire down here and wrap it like this. Don't worry about the number of turns or anything. Anyway, if you have a current if you have a current I here flowing in, you assume it, you dot the terminal, right? How many remember this? I think all of you should from physics even. So if you want to know the direction the magnetic flux created by that goes, you take your right hand, assuming you have one, put your thumb in the direction of the actual, or I should say, put your index finger in the direction of the current, right? And your thumb points in the direction of the flux. If current's going that way, flux is going up. Do you all follow me in that? How many? Remember that, everybody? How many did? It's a standard way you figure out the direction of magnetic flux. If current's going in that, and I'm dotting that. Now, in the second one, you choose a terminal. Doesn't matter. And dot. And here you put another current going in there. And if the fluxes are in the same direction, they're additive, and that dot stays there. Do you all remember that? Gross used to talk about that. I think Charlie still does. See, Dr. Gross. How many have had him again for this thing? He's he's emphatic. He goes through, he probably calculates the inductance for the number of turns and all that. This is assuming it's iron core, it's ferrite, and it's infinitely long, and all the flux is coupled. But that doesn't matter. That's what happens. Now, if by chance it was wound in a different direction, all right, suppose I took and I dotted this terminal, and I put current in here. All right? Well, then you can see that the flux would be down. Do you all agree with that? And if you get the fluxes that aren't in the same direction, you erase that dot and put it on the other terminal. That's the bottom line with the dot convention. The flux is added for the currents entering, the dot stays. If they're opposed, the dot is reversed. Okay? So that's how you do it. So this thing right here is basically a winding. It's a transformer. And you think about this, there's N turns. Don't worry about that right now. Got a current going in. The fluxes are additive if you look at this, aren't they? The current swirling around that way, the magnetic flux for this one is this way. Current swirling that way, magnetic flux is this way. Do you all agree with that? So that means you did it right. You wound them in the same direction the right way for a common mode choke. The next thing you have to do is understand that between here and here, right there, we really have a transformer, all right? if you want me to, and I want to do it this way, Dr. Whitmore's book didn't show you this, but I'm going to, because I think it will make things more understandable. So if I take a look at that, and now I'm going to say, well, what does this look like? And I won't say a transformer, pardon me. I'm going to call it a magnetically coupled circuit. Y'all have magnetically coupled circuits, right? How many had transformers? Did you not have transformers? Who did not have a transformers? Transformers were magnetically coupled circuits. Everybody in here should have, right? Because they're essential parts of circuits. I don't know if you get them in your basic circuits courses or if you get it in a different course, but transformers and magnetically coupled circuits are essential. And in general, what we've got here is this. We've got a coil here and a coil here. All right, this coil has some L1. I'm going to call this L1 too. They're always the same number of turns for common mode choke. If you don't do that, you're hurting yourself. All right? So the same number of turns, it's an identical core, everything's the same. There's going to be a current I1 coming in here. And with magnetically coupled circuits, there's a current I2 coming in here. And there's something called a mutual inductance. So I'm labeling that as N. Do you all remember M? Right? Now, the thing about this, because this is going to be a ferrite core, and these are going to be a fair number of turns, 50, 100, something like this, that you can pretty much say that the mutual coupling is about the same as the actual self-inductance. The mutual inductance is going to be the same as the self-inductance. L is a symbol for inductance, all right? So when we have current I1 here, we develop a voltage V1. Current I2 there, you develop a voltage V2. You all agree with that? I'm going to do this in a phasor domain. Well, how do you get the voltage? Well, from magnetically coupled circuits, the basic theory, you remember that the voltage V1, if it was just an inductor, it would be J omega L, right? In this case, L1 times I1. That would be the voltage right here, caused by that inductance with the current flow, right? But there's a reflected inductance from this, or reflected voltage, I should say, from this one, that's going to be plus J omega mutual times I2. Now, if there is no I2, it's not a problem. It doesn't exist. Do you all agree with that? And then you say for V2, same basic things, J omega, but now it's going to be M I1, because now when you're talking about the voltage here, the first term with I1 is going to be the mutual reflecting that voltage developing. And it's going to be plus J omega L1 I2. Now, I'm using just L1 to indicate the self-inductance of those terms. They're going to be identical. That I can assure you of for any common mode choke. All right, now we have to take a look at how a common mode choke will block common mode currents, but allow differential mode currents to flow. And here's how. This is the picture you got in your mind. So when I look at V1 right here, now here's the idea. I want to make sure I stop common mode. Follow me? Common mode would be when I1 and I2 are the same direction. Remember the way I drew that? I had a primary core and then a secondary core beneath it, right? So when I look at this, if I say for common mode choke in the common mode, write this down. And that means that I1 is equal to I2. In other words, for that little picture I did, I'm not going to draw the whole thing. That means I1 here would be in the same direction as I2, or basically, you have that. Do y'all follow me on this, class? Okay? Well, if that's the case, what is V1? Well, V1 would be equal to J omega L1 I1 plus J omega M I2, or it would be J omega L plus M, and this is L1, times just I1. And you can call that I common if you want, since they're the same. It doesn't matter the term here. Now, when I look at V2, it again will have the same form. It'll be J omega M I1 plus J omega L1 I1. Call that I1. And that will be equal to J omega L plus M times I1. You all follow me? Now, here's the point I'm making by doing that. And I spend a little more time on this because there are people that really confuse this. This is a magnetically coupled circuit. It's not an ideal transformer. It's close, but not an ideal. When I take a look at this, doesn't this V1 look like just an inductor of value L plus M? You all see that? So if currents are common mode, what the common mode choke will appear as, here's the first set of windings. It looks like L plus M is the inductance. And the second set of coils will look like L plus M2. This assumes the current's going in the same direction. All right, coming out this way. Okay? So now the natural thing is, well, how much impedance do I have to current flow? You all agree with this? We could get the impedance per coil. It would be what? Just J omega L plus M I1 here. That would be the impedance, right? If I wanted the voltage drop, I would take that current times that impedance. Do you all agree? And same here. With me? So the net effect, if we had a circuit and we were worried about common mode, would be, you could look at it like this, or you could say the impedance of one coil was equal to J omega L plus M. With me? This is common mode. Currents flowing, and you're thinking, well, currents never flow in the same direction. Believe me, they do. All right, unintentionally, not because you wanted it that way. What happens is if you have magnetic loops, any kind of a loop of wire, say you have an extension cord and you got a big loop of wire, and you got the extension cord going into the wall. Well, if there's a time-varying magnetic field here, it drives currents in the same direction in both of those wires. And in fact, it will be common mode, and that will cause all sorts of disruptive problems. I'm just telling you, anything that can go wrong will go wrong if you don't shield for common mode with electronic equipment plugged into wall outlets. Okay, and frankly, I'm not an expert in mitigating all forms of EMC, but I'll tell you, common mode is an easy thing to take care of if it's not lightning related. Now, if it's lightning related, I'm just going to tell you, this won't touch it. What you have to do is when lightning is sensed, the voltage goes beyond a certain threshold, you have to short that thing to ground. You have to basically induce a fault or you'll destroy your system. A temporary short-term fault. And that's what power companies try to do on all of their power lines. You had power, right? You didn't have power yet? How many had power? Did Gross ever talk about, or whoever he had helping, lightning protection or anything like that? Faults? Did he talk about faults? Short to ground? Okay. Well, faults are important. All right, so that would be the impedance of the coils. You would have twice that of two coils in differential mode, but this is in common mode. Only one coil you're worried about. Now, if it's in differential mode, that's common mode. I'm going to go here. So when we talk about differential mode, that means we have currents like this. If this is the primary, right here, this is the secondary. Now I have a current I, this is going to be I differential. I1 equals minus I2 in opposite directions. You have I differential that way, I differential that way. We're going to find out what value we actually get here. And I think it's, by this time you're probably going to see, I'm trying to find out the value of these coil and inductances. Well, I'm going to go back to this equation right here. And the only thing I'm going to do is modify one thing. Just hear me. I want you to all hear me. When I have this equation, and I'm in differential mode, it's still J omega L I1 for the first part. But the second part is what? minus j omega m I1, right? Because now the currents are in the same magnitude, opposite directions. Does everybody follow me on that? What about down here? This becomes a -2. Well, it would be j omega m I1 or not. Well, it doesn't actually make sense. You can put, technically speaking, the j omega L I1 would be from secondary. That would be positive. This would be minus. This is for differential mode. So it would be L minus M again. So when you have currents in a differential mode, the effective impedance would be j omega L minus M, or really these coils look like an impedance of L minus M. Are you with me? Now, if you think about the difference in impedance, here, we take a look at this. If L is almost M, the differential impedance is 0, isn't it? Y'all see that? So if currents are trying to go back and forth through that transformer in opposite directions, right? There's nothing stopping them. If L gets close to M, and in the real world, L becomes almost identical to M, so they don't stop differential currents. But what happens in common mode? Well, then I'm going to have j omega L plus M, right, for just one coil. Now just think about this. If we're at megahertz, just go with megahertz. Right? You got a megahertz signal, that's 10 to the 6. J omega, that's 2 pi times 10 to the 6, right? Call it 6 times 10 to the 6, just for kicks, right? 6 times 10 to the 6 times L plus M. Well, if L is millihenries, right? Then you've got, what? You got thousands of ohms of impedance stopping the differential, or stopping the common mode current. Y'all with me on that? And I'm going to level with you. I'll give you a few problems so you can feel this thing out and feel better about it. But here, when you're doing this stuff, the key to remember is if you're in differential mode, the coils look like L minus M. Both of those coils. If you're in common mode, they look like L plus M. And that's it. I'm not going to ask you to calculate the inductance. In EMC, we might do some estimates of inductance when we actually wind them, but here I'm not going to. I'm just exposing you to it. You with me? I'll give you problems I think you can handle. Member's book is extremely sparse on this, but I want to make sure you understand the reasoning behind everything we do. And by the way, magnetically coupled circuits are not something that, generally speaking, a non-power engineer just delves into. Usually if you're in power engineering, you're going to be dealing with things like that. So that's another reason I don't go into real detail about how to calculate the mutual and self-inductance of something wound on a donut. But that's, y'all know how to calculate inductance for a long wire, with loops of wire over a ferrite core. Didn't you all do that stuff back in EMAG 1? Mm-hmm. Remember you calculate capacitance, it was what? For parallel plate, it was the area of the plate, right, times epsilon divided by the separation distance for a simple parallel plate. What about an inductor? Well, inductance was what? It's n squared, you know that. Number of turns goes up by the squared, right? And then it's a ratio of length, right? The length divided by the actual core area. But I'm not going to go there now. Just realize in the real world you should have at least some intuitive understanding of what the estimates are for parallel plate capacitors or just generally capacitors and what they are for inductors. Yeah.
So the chokes, where are they practically? Where do they place those on, say, power?
Good question. Right off that extension cord. Coming off that extension cord, that's AC, right? You want AC, don't you? You take a common mode choke there. You could, if you've got problems with common mode, that will stop the common mode currents from flowing, from causing disruption, all right? Now, there's something else I didn't say. Whenever you're talking about currents coming out of that wall that are fairly large, you got to make sure your inductor doesn't thermally heat up and catch fire or melt or something like that. So you have to calculate the losses involved through that wire. That's going to be resistive losses, and there are ferrite called hysteresis losses in the core material. Some of you have heard about. This is a little beyond the topics that we're going to cover, but that's the commonplace. You can also, in your circuit, now remember this, when you have circuits, especially things that I deal with, like radar circuits, Any kind of disruptive noise, anything at all, will cause a huge problem in seeing the signal. Anytime there's a possibility of a common mode current, you're going to put one of these common mode chokes, and that would be out of the power supply inside a radar unit. But for the most part, common mode chokes, if you look at where they're used, right off the wall out. And that makes sense, right? Into a wall or out of a wall is where you want. And I say that, I think of all these things I should qualify that statement with, but that's generally true. Does he have anything in his book about where it's commonly used? I looked through that, I didn't see anything that jumped off the page. Now when I teach this in the EMC, it gets much more developed so that you can design a practical coil for whatever your problem is with real materials, but at least I can do that.
Just power lines.
Yeah, well, to me that's a power line. All right, if I don't. You can ask Dr. Grosses or Dr. Halpin or Dr. Nelms. I don't know of any common mode chokes that are used on the large lines and that are up to 7,200 volt lines or higher. Frankly, because the voltages they got are so large, you don't have to worry about ground loops and stuff. But the second thing too is the only real problem you're going to have is lightning, and when it's lightning. Anytime they sense lightning, what they usually do, it triggers something, it'll put a direct short to ground and take the actual circuit offline for a second. Because that's the only way to deal with lightning. Y'all know that, guys? By the way, I'll just tell you the last story if I have it. Did I tell you about a student I had named Paul Ryan, what happened to his father's house? His father worked for the power company. He had bought lightning protection equipment, it was out in the yard. And I was teaching this course, and we were in EMC. And he came to me, he came to me after class, and he said, you know, Dr. Baginski, all around the house, it's his dream home. It was his retirement. But it's on a mountainous area that's it's got a core of rock, so it's like not very good conducting, right? And insulated. He said, lightning struck around that. As a matter of fact, it's hitting, I've seen pieces of concrete blow up. Now that means the rebar itself thermally heated to a point which sheared the concrete. I'm like, God, you better get some. I told him this directly to him. I said, you need to get some lightning protection up there. Tell your father immediately. So he works for the power company. He's got it in his yard. And they're, well, you know, if you got it in your yard, you need to put it up like today because things can happen. This is the true story. Before the next class period, as I recall, I'm not trying to sensationalize. I get a call. So it would be like a Thursday afternoon if it's a Friday class. And he says, our house is on fire. And they're, what? There was a thunderstorm. Got hit by lightning. It's on fire. Oh, I'm so sorry. So I went out to see this. I wanted to see the damage, the lightning damage. So we're out there, and all of a sudden, it sounded like a machine gun fight. He had these ammo boxes. And I don't mean a few. I mean, these guys are hunters, you know, sports, skeet shooters, stuff like that. It sounded like a war. And you talk about firemen and everybody running out of the place. As soon as that gunfire starts, everybody is running for their lives because it sounded like somebody had a machine gun and they're just blasting away at us. And then you hear nothing for a second. You think, okay, you can get closer. Then all of a sudden, bang, bang, bang. So I learned a lesson about lightning protection from a student of mine. If ever I think it needs to be done, it needs to be done now, not a day later. And that's a true story, too. And a common mode choke ain't going to hurt that, or help that, but I'm going to tell you lightning protection will. And you know the best way to do lightning protection from what? I mean, cheap way? The only thing you do is take a wire. It's called a cone of protection. I forgot if it's a 30-degree angle. And everything under there is protected. You hang a guy wire as thick as you can. You know, make it as thick as a grounding rod if possible. Take it, just hang it over whatever you want covered. It's got to be up there so you've got a 30-degree cone, I think it is. And then take that and just ground it. Now, I tell you, you can do it if you have to, but here's the bad thing. When you're in areas that get hit by lightning that are like high up with rock under them, if you ever have like, I don't know, shed stuff like this, do it, because if you get hit by lightning in certain things, I mean, if it hits, it can kill you possibly, but it can surely destroy the structures. So just remember that. Okay, we're basically done with chapter 9. Now, Next chapter is going to be Next chapter is going to be microwave, chapter 10. And with microwave engineering, when I think of microwave, I think gigahertz, typically. People may argue, but if you're going from about gigahertz, low gigahertz, maybe 800 megahertz, all the way up to 80, 90 gigahertz. Give you an idea what we're talking about frequency-wise. Police radar units around here are Ka-band. That's about 33 to 36 gigahertz. There's a general K-band is 24 gigahertz. There's a Ku that's 18 gigahertz. The old X-band units were about 10.45 gigahertz. We're talking about gigahertz stuff. When we do engineering with gigahertz stuff, our wavelengths are small, so we don't assume a wire, just two parallel wires, are just good conductors. We have to look at them as transmission lines. You all follow me on this? Because the wavelength gets so small. So in general, first thing I want to say is when we talk about microwave engineering, generally we talk about 1 to 80 gigahertz, something like that. It could go 88 gigahertz. There are radars that are probably a little slightly higher than that. These radars are these type of signals are used primarily to communicate through the atmosphere, and generally for radar work, microwave engineering. There's microwave links for all sorts of stuff, but that's generally, so when I think of microwave, that's about up to 80 gigahertz, 1 to about 80 gigahertz. So how do we get this signal back and forth? Well, first, here's the thing we look at. The type of structures we use are called strip lines, and they've got other designations. Now I'm just going to tell you what this looks like. You remember that FR4 board you used, that green board? Didn't you guys have to do some kind of a lab with a green board or not? No? How many know what FR4 board is? How about Duro board? If you don't, that's okay. Only thing they're called high frequency laminates. They are simply a piece of copper. This would be a typical, call it Duro board. This is a typical one. And this is a low loss, so it's expensive. They're about $100 a square foot. Now they're very thin, but they have copper on top. So this will be copper. Then below them, they're going to have a dielectric material with some value epsilon. That value epsilon is going to have almost no loss. You know how generally epsilon will have epsilon prime plus j epsilon double prime, and the double prime is the lossy term. They have almost no loss right here. And then they're going to have a piece of copper down here. Looks like a capacitor to me. This is going to be a distance d thickness. And here's what they do. Now remember, this board is in 3D, so it's got depth like that. I'm not showing that very well, but go with me on this. Here's what they do when they make circuits. This is going to be at a very small level, by the way. What they'll do is this. They're going to etch off everything but something that's got a certain line width like that. So if you're looking down the barrel at this thing, they're going to etch off all the copper except the copper they want. And it'll look like this. It'll be a line with a width W, a thickness T, and there's going to be a height H, some epsilon relative. Usually epsilon relative is the only thing you need because it's low loss. And you got this line like this, and there's copper down here. So when you put a plus to minus voltage here, this thing just looks like an extension cord, like a transmission line. Y'all follow me on this? Currents go down the one part, come back the other part. This looks like a big flat conductor, but it's long. So because it's long, and remember this is high frequency, so in general when you have a line length, this is important here. Line length L greater than lambda over 10, you need to do microwave engineering. Now it doesn't look like just a short connection. You know how you do all sorts of soldering with leads and you assume that that thing's basically a perfect conductor, right? Now when this thing becomes the length of these lines, and length is this direction, that would be the length. Or length, that one. Whenever those things become longer than a tenth of a wavelength, now you have to do microwave engineering. And then it looks like characteristic impedance of a transmission line. You all remember that, right? So we're back to where we started. So in Dr. Wentworth's book, I want to just tell you this. If you have it, let me have this book here. If you got it, I'm going to just tell you right now, I don't worry about a lot of things about capacitance and characteristic impedance of lines by estimating. So let me just get to you. 544. 544? Let's see. So if you look there, what I just drew is basically on page 544.
Or 533 is what you just drew.
Well, 544 is better. And what they do is they show you basically what I did, where you're going to have field lines that are just from the plus to the minus charges. He's just trying to give you an idea of what happens inside one of those. Now, most of the power and energy, when I say most, probably about 95%, is all inside here. The thing is not propagating at the speed of light. It'll be propagating at a reduced level. It'll be about C over the square root of what they call an epsilon effective. You don't have to know this well. This is equation 10.1. Now, characteristic impedances for these things. I wrote a paper. There was a paper published years and years ago. And what we did is we found out how the characteristic impedance varies as you get closer to the edge, and we developed a family of curves. So we had for any spacing distance h ratio to w for all the primitivity possibilities. We showed families of curves, and then we developed equations that approximate it. That's what engineers do. They find a method for giving somebody who's a designer, if he wants to know the characteristic impedance of that line as you're moving close to an edge, you can estimate. Or maybe you want to design to prevent it. But anyway, we did this and we published it. When I was doing that, I saw all these equations. You can look at some of them in 545, on page 545, equation 10.5 and 10.6. And you'll notice these things don't look like they came out of Maxwell's equations. They didn't. They're based on measurements. All right? They're based on experimental data that they curve fit. That's the only thing. There's a million of these. These are just a couple. There's a whole mess of these things that are out there right now with Mentor Graphics and all these other software programs that people use to design. Nobody goes around, that I know of at least, and calculates the values in 10.5 and 10.6. It's nice to know how to do it if you need an approximation, but the truth of the matter is there are so many, even online, I bet you could find simple microstrip tools where you put the ratios of the different parameters, or just put in the parameter values in epsilon, it'll bang, that's the impedance. Or if you want an impedance and you nail down 4 of the 5 things, it'll give you the other thing. So that's the deal. Now here's the thing about these impedances. This is so important. Remember I said as you move closer to the edge, all of a sudden the characteristic impedance of this line is going to change, right? Well, that's real bad. All right, because when a characteristic impedance changes, all of a sudden you get reflections. You don't ever want that. So when you design these things, you would like to make sure that all the lines that you're designing that are going to be good connectors aren't near the edge or aren't near something that's going to change the impedance significantly. For instance, a big chunk of metal. Y'all with me on that, guys? You don't want that. That's just something to keep in your mind if you're ever looking at a circuit board and trying to figure out what might be wrong with it. And if that's the case, now the way you do business is what I'm about to show you. Thank God you've had most of this earlier. You've had transmission lines. So here's what happens. And the best way to do this is just say, how do we represent a transmission line? Doesn't matter the geometry, it's two wires, isn't it? And it's got a characteristic impedance Z0. So now we're going to talk about something in the microwave realm. This is impedance matching. And we're not going to use stubs. We're going to use actual elements. You know why we don't use stubs? What is a stub in general? It's a length of wire that's got either a short circuit or an open circuit on it, right? That you put in parallel or series with a load to achieve impedance matching, right? But what's the problem with a stub? It's long, all right? And even if we're talking about wavelengths that are small, when you talk about the topical surface area of something you're designing, like a Doroid board or an FR4 board, anything is too long. So what they'll do is design around very small components, capacitors and inductors, that they can just take and just press in there, and it'll have virtually no real footprint, no additional footprint. Because when you have a microstrip, there's a lot of things they don't tell you until you have to work with these things. You got to put a line in. I mean, you're going to have to put something. You got to put a short on the end of it, all right, or an open. Typically a short, so it doesn't radiate. And then, or I should say, interfere with other things. Then after that, you got to make sure nothing's nearby that could be affected by that. With me? So you might have to shield it even. And it's a pain. That's the reason they use individual elements. So what they're going to do, this is the way they do it. We're going to start with an impedance here. All right. And I'm going to draw a Smith chart for you. Y'all remember Smith charts? All right. You start with, this is the way I always draw them. Draw a big old circle, like so, and then put an equator. All right, something right through the center. That's not drawn symmetrically, but I'm trying. All right. Then after that, you find the center of it, about here, and you draw what's called a one circle. This is the R equal 1 circle. Do y'all remember that? Now, in general, if we wanted to use one of these things, you would take the characteristic impedance, or the impedance of your load, divided by the characteristic impedance, and that would be the first point that you plot on those, right? We know that there's imaginary terms here. This would be J1. This would be minus J1, right? And we know that these represent reactances, right? Either negative or positive reactances. And any circle any concentric circle like this represents just real values of the normalized impedance, right? You with me on this, guys? It's been a while, I know, but most of you do understand. So you're going to get this. I hate to say this, but in the real world, even vector network analyzers, from what I'm told, well, the HP ones, they still come up with a Smith chart when you do measurements and impedance matching and stuff. So it's ubiquitous. You can't get rid of it. You're going to be dealing with Smith charts. Now, this right here, that's the R equals 1. But if we take the mirror image of that and put it here, that's the rotated circle. It's literally just taking this thing at the center, unhinging it, and pressing it on the other side. Here's why we do this. All right? Just listen. Anytime we're on the edge of either of these two, well, preferably this one. If we're on the edge, if we've got R equals, say, we know it's R is 1, right? If I have 1 plus J 50 ohms, what do I need to, or 1 plus J5, let me do it that way. All right, normalize them. If I want to match that, I just put an impedance in series with it of minus J5, right? And normalize the impedance. You with me? And then I get R equal 1 and it's matched and I'm happy. Well, the neat thing is, any point here that's an impedance has a reflected value of admittance here that's on that rotated circle. So another thing I think about is, hey, if I do impedance matching, if I can get something to the rotated circle, and I, in other words, add something so that the total thing will be on this rotated circle right here, which does not have a good equation. I just want to tell you that. Yeah, so you physically, I'll send you something to draw it. Matter of fact, can you send an email to make sure I send rotated Smith charts? They're in a book, but I want to send them to you so you can print them out or use them on your tablets, okay? Then I can do impedance matching. So how do you do it? And here's the bottom line. First thing, just like any other thing, you find the load and divide it by Z naught, get the characteristic, or get the normalized impedance, okay? Plot that point. The point can be in three places. Just listen to me, I'm going to go through this again, but listen. The point could be in here, inside the one circle, right? The point could be here, inside the rotated circle, or the point could be outside of both. You all follow me? Three possibilities. And for every one of these, we deal with this slightly differently, but our goal is to get impedance matching. So here's what happens. I'm going to do this with an example. By the way, there's a rotated Smith chart in his book. What page is that on? He's probably got a project.
It's 552 or 553. It's like
Tell you what, you can go right to 553 and just look there for a second. That's the one I'm going to use. But I want to do it up here and talk my way through it, okay? So let me get rid of this. How are your classes going so far?
Good.
I'm just curious. I've been hearing a lot of things about classes and online, and students have had enough. So, some professors like them. I don't. I hate it. I use the board. So when I take a look at this right here, our best way is do an example. So we're going to assume the load impedance is going to be 250 minus J250 ohms. And we're going to assume the characteristic impedance of the line is 50 ohms. That's probably fairly typical. Something you need to impedance match. The 250 minus J250 could be an antenna, to be honest with you. It's in that range for some. You want impedance matching. So first thing I do is find out what ZL is. ZL would be equal to the normalized load impedance would be ZL over Z naught. And that's 5 minus J5, right? Correct, class? All right. Now, where does that occur? Well, if that's the one circle here, 5 minus J5, the 5 circle is probably here, right? And the minus J5 is somewhere down here. It's probably like right here. This would be normalized ZL, which would be 5 minus J5. Can y'all locate that in the book? Just take a look if you got your book. It's inside the one circle. It's something, I mean, can you see it? Is this not minus? Where is it?
Let's say minus.
Oh, wait a second. Yeah, I'm sorry, I guess it's this one. Look at page 553. It's the first example, so I'm not sure which of those corresponds to.
Hold on, I'm not making it.
Which page is that?
This is, so this is for this.
Okay, so it's on page 555. All right, so this is his point 1 right here, 5 minus J5. Now, that point lies within the one circle. Here's my point here. Now, take a look at this. If I have 5 minus J5, if I get rid of the minus J5, I still have a real part of 5, and that means it's not impedance matched. Because even if I get rid of that minus J, the real impedance would still be 250 ohms, right? And I got a 50 ohm transmission line. So there's nothing I can do by adding an impedance in series. But if I go to the admittance domain, remember, now I'm going to take 1 over, now I'm going to get YL here, normalized, which is going to be 1 over ZL. And here I get 0.1 plus J 0.1. Do you all see that in the book? By the way, if you don't have a book, go with me on this one. I'll try to be as clear. Can you see it too on your laptop, I think? Are you looking at that example? Oh.
No.
Well, anyway, what I want to tell you is that this is YL. Now all right, we went from inside the one circle. Anytime you're inside the one circle, you got to get outside of it. Now we're outside of it, all right? We're over here. You with me? Now, when you're outside of it in a rotated circle, that's the admittance domain. That's a Y domain. What do you know about admittances? If you want to add admittance, you add in parallel, right? Correct, class? So here, first thing I'm going to do, I'm going to add admittance in parallel. And I want to go to this edge. Do y'all follow me? With me? I want to get either add something and get here, or add something and get here. And I didn't show this, but there's a giant circle right there that's R equals 0.1, right? It's the one that looks like that. And here I am at 1 plus J1. I want to get to this point. So if you go on the 0.1 circle, you're going to find this point is about what? 0.3, or 0, yeah. The point right here is going to be 1 plus J 0.3. Take a look at it. Isn't that about right, class? Can you see it?
Mm-hmm.
Yeah, oh, he doesn't have the line.
It would be about there though.
It will be about that. Now, that means here I was at 0.1 plus J 0.1, and I want to get to J 0.3. You're all with me on this, right? I have to add J 0.2. Agree? All right. So what I'm going to do right here is say I'm adding an admittance of J 0.2 here. That's an admittance. Admittances will always be in parallel. It's a normalized admittance. I'm going to get to what the values are in a second. All right. Now when I do that, I'm at this point. I went from point 1 here to point 2 here, then to point 3 because I added on that J 0.2. Can y'all follow me on this? That's an admittance. I'm over here at this point 3. And whenever I'm on the rim, I'm basically the problem is done. Now this is still admittance, right? Now I go back to the impedance domain. Here. And I get 0.4 right here. And 0.4 is going to be 1 minus J. And I wish I remembered it. Three. 1 minus J3. Take a look. Can you all see this point right here? This is impedance, normalized impedance. Right here. Do y'all see that, class? Yeah.
It's been a minute since I've done this.
Say again?
I said it's been a minute since I've done this chart. Why are we trying to move from the Y to the 1 plus J.3?
What? Well, I know if I can get to the rim of this rotated circle, I can get to the rim here. That's where I want to go. Because this is admittance, this is impedance. They're the same point spatially. All right? If this is the admittance of a point, this would be the impedance. When I'm there, now I got 1, the real part, plus or minus J something. I can add a series impedance element and get rid of that J something. Y'all with me on this? That's the reason we're doing this. Okay?
So how do we know it's that point?
Well, if you take 1 over this, you can do it yourself. 1 over 1 plus J.3, you'll get 1 minus J3. You go ahead and do it. It's just 1 over that, right?
Okay.
All right. Y'all follow me on this? Another way to do it is just take your ruler and draw a straight line from this through the center of the circle, through the 1 circle, and the 2 points that intersect here and here will be YL and ZL, or the impedance, or the admittance, okay? With me? It's not hard, really, if you follow what's going on here. So now I'm down here and I have 1 minus J3, right? This is an impedance. Well, I got to get rid of that minus J3. What do? We add J3, right? In series. Do y'all agree with this? So this would be, now remember, this is an admittance. Now we're going to add an impedance here of J3. And that is a Z. So now I talk about what components are in terms of admittances and impedances that are normalized. Because so far I just gathered you values that have got J3 and J0.2, It doesn't tell you anything about the actual value of the component, the inductor or the capacitor. So here's how you do it. You start with a basic, try to get this image in your head. There's the value of C here. We know we have a current I, and we develop a voltage V. And in general, when we talk about something like this, we say this has an impedance, and I'll call it impedance or Z here, of simply 1 over J omega C. Y'all agree? That's the impedance of the capacitor. Really, it's minus J, right? This would be Z of a capacitor. Or it would be minus J over omega C. Now that's the impedance of a capacitor, right? If you normalize that impedance, this would be normalized, it would be Z sub C over Z naught. It would be minus J over omega C times Z naught. That's the normalized impedance. Do y'all follow me? Okay? I just took the value of impedance, divided by Z naught, it's normalization is what it's called. All right? Now, what's the normalized admittance? Well, that would be Y sub C is 1 over Z sub C normalized, and that would be equal to, that's equal to J omega C Z naught. Are you with me? For a capacitor. That's normalized impedance. That's normalized admittance for a capacitor. Y'all with me on this? You remember admittance in impedance, right? Impedance is 1 over admittance and vice versa. All right, what about an inductor? Well, if you have an inductor, right, with plus or minus V, current I, then you find out that the actual impedance of the inductor is J omega L, right? The normalized impedance of an inductor is J omega L over Z naught. And the normalized admittance of an inductor would simply be 1 over this, or Z naught over omega L with a minus J. This is just 1 over this. Y'all with me? Now, here's the deal. This admittance is 0.2, right? Right there, y'all with me? Well, if I got 0.2 here, it's a plus J. I know the normalized admittance of the capacitor's got a plus J. With me? So now I set that 0.2 equal to omega C Z naught. Now, does everybody follow why I did that? Because I know I need to calculate the value of C, and I find from that C is equal to 0.2 over omega, right? Z naught. You all agree? Now this one's got an impedance of J3 normalized. Positive J is inductance, right? So what would this 3 be, or I should say J3? Well, 3 would be equal to, or J3 would be equal to J omega L, right? Divided by Z naught. Do y'all follow me on this? With the impedance of an inductor, J omega L, divided by Z naught. Now I have the normalized impedance done. And I have to set that equal to 0.3. And therefore I can see that the value of L that would solve this would be what? 3 times Z naught here, right? Divided by omega. Do y'all agree with that? And that's how you do the values themselves. Now I didn't get to this point, I'm over, but let me just finish my thought. If you're inside the rotated circle, with your impedance, suppose your impedance is inside the rotated circle. Well, there's nothing you can add to that impedance to get to the rim of the other one. So what you have to do, I better tell you what, I'll go through this one with you. But basically what you're going to end up doing is instead of adding admittance, you add impedance first. All right, you add impedance, and then When you add impedance, you get to the rim and go back to the other domain, and we'll do that next time, and then I'll show you. The nice thing is if you're outside either the rotated or the regular arc one circle, you can do what you want. If you want impedance first, you can. If you want admittance first, you can. It doesn't matter, because you can do it. And I'll take you through that example. We'll finish this up Friday. I'll give you some homework. Go with me on this.